Hey everyone, welcome to this explainer. Okay, I am absolutely thrilled to have you here today because we're going to explore this totally hidden piece of infrastructure that is quite literally protecting our modern electrical world every single second. Most of us, we flip a light switch or plug in a phone without ever really thinking about the massive, roaring rivers of electricity flowing through our city's grids. But what keeps those rivers from just overflowing and causing catastrophic damage? Well, today we're decoding the ultimate electrical bodyguard.
I mean, really think about that for a second. How do you safely stop a 36,000-volt power surge in a literal fraction of a second? When electricity at that kind of voltage decides to jump out of its designated path, it doesn't just spark. It creates this terrifying, blindingly hot plasma arc that can literally melt metal and start massive fires. Stopping that kind of raw, destructive energy requires some truly brilliant engineering. And that brings us to our technological hero.
Okay, let's dive into this. Here is our roadmap for today. First, 1. Know the vacuum circuit breaker. 2. Advantages and main functions. 3. Anatomy of internal mechanisms. 4. Circuit breaking process. 5. VCB types and installation. And finally, 6. Applications and safety measures. All right, jumping right into section 1, know the vacuum circuit breaker. Basically, what actually is this thing? At first glance, looking at the underlying blueprint for this technology, it's a massive wall of technical data, right? Complex schematics, tiny mechanical parts. It can definitely feel a little intimidating. But don't worry, we're going to systematically decode this whole thing together. We'll break it down piece by piece until you completely understand what's going on under the hood.
So what exactly is a vacuum circuit breaker, or a VCB for short? At its core, it's a heavy-duty switching device. But unlike that simple light switch in your kitchen, a VCB uses a pure vacuum as its arc-quenching medium to safely break and connect high-voltage electricity. Since a vacuum is completely, utterly empty, it provides exceptionally high insulation. When a highly energized connection is broken inside that vacuum, the resulting electrical arc is extinguished almost instantly. This makes the VCB totally perfect for critical systems that demand high reliability and low maintenance.
And just trying to wrap our heads around the massive scale of power this device handles is kind of crazy. A standard VCB operates at rated voltages anywhere from 3.6 kilovolts all the way up to an astonishing 36 kilovolts. Guys, that's 36,000 volts. It can carry a rated current of up to 4,000 amps and handle a short-circuit breaking current up to 50 kiloamps. Operating at standard 50 or 60 hertz frequencies driven by these really powerful spring or motor mechanisms, these specs just highlight that the VCB isn't just a switch. It's a heavy-duty industrial powerhouse. Moving right along to section 2, advantages and main functions. Why choose this specific tech? Now, what's really interesting about this is the environmental and safety impact. Back in the day, heavy circuit breakers usually used flammable oils or this incredibly potent greenhouse gas called SF6 just to quench electrical arcs. VCBs? They don't need any of that. Because they use a pure vacuum, there's literally no oil to catch on fire and no toxic gas to leak out into the atmosphere. This makes them incredibly eco-friendly, remarkably safe, and highly reliable. Plus, without oil or gas to constantly replace, the maintenance costs just drop significantly. So, taking all those advantages into account, its main function becomes pretty obvious. Its primary job is to act as an automatic, rapid response bodyguard against overcurrents or short circuits. If it detects a problem, boom, it breaks the connection instantly. This extremely rapid response protects millions of dollars worth of downstream equipment and heavy cable networks from basically melting or catching fire, guaranteeing the safety of the entire power supply network. All right, section 3, anatomy of internal mechanisms. Let's engage our X-ray vision here. Looking right past that heavy metal casing, inside the VCB, there's this beautifully choreographed mechanical dance going on. Electricity flows through the fixed contact and the moving contact. That moving contact is driven by a powerful operating mechanism, usually a heavy spring or a motor. Protecting the core, we have a metallic shield and bellows keeping out dust and moisture while letting the parts actually move. And on the outside, a clear indicator lets operators know instantly if the system is on, off, or has tripped due to a fault. But the absolute star of the show is part number 3, the vacuum interrupter. This is the absolute superpower zone of the VCB. When those highly energized contacts pull apart, the electricity desperately wants to keep flowing, right? So it creates an arc. In normal air, that arc would burn incredibly hot, ionizing the air to sustain itself. But inside the vacuum interrupter chamber, there is nothing. It's exactly like the vacuum of deep space. No air, no gas, no molecules to ionize. Stripped of the medium it needs to travel through, the arc simply cannot survive, and it's starved out of existence in literal milliseconds.
Which leads us to section 4, circuit breaking process. Time to see this in motion. Let's move to and see how this builds, basically watching a split-second electrical fault in ultra-slow motion. Step 1. In the normal state, the moving and fixed contacts are touching, and current flows smoothly. Step 2. A fault occurs. Say, lightning strikes somewhere. The protection system instantly detects the massive overcurrent and fires a command to open. Step 3. The breaking process. The mechanism violently pulls the moving contact away. An arc forms for a fraction of a second, but trapped inside that vacuum chamber, it just instantly vanishes. Step 4. Open circuit. The connection is completely severed, the current is stopped dead in its tracks, and the whole system returns to a safe state. All of this happens way faster than you can blink.
Okay, Section 5, VCB types and installation. Let's look at the real-world habitats. Generally, you're going to see VCBs in two main form factors. The fixed type is exactly what it sounds like, permanently installed right into the switchwire panel. These are usually much larger and built for incredibly high capacity. On the other hand, the draw-out type is mounted on rails or wheels. This design means the entire heavy breaker unit can be physically rolled out of the panel for inspection and maintenance. So it trades a bit of that permanence for incredible flexibility and safety. For those draw-out types, engineers actually use 3 distinct physical positions to interact with them safely. In the connect position, the breaker is fully pushed in, making contact with the high-voltage bus bars. It is live and operational. In the test position, it's pulled back just enough to break the main high-voltage circuit, but the low-voltage control wires stay connected so engineers can test the mechanical tripping safely. Finally, in the isolated position, the unit is pulled out completely, entirely separated from all power for full hands-on maintenance. Finally, Section 6, Applications and Safety Measures. Let's connect this back to your daily life. Because, these VCBs are actually living right in your neighborhood. They're the hidden guardians inside electrical substations. They manage the massive power loads in industrial plants and those high-rise office buildings downtown. They protect critical infrastructure like the MRT train systems you ride and the airports you fly out of. They even stand guard in hospitals, making absolutely sure that life-saving medical equipment doesn't lose power during a surge. They are everywhere, quietly keeping modern civilization humming along. So the crucial point is, despite their brilliant design, VCBs are incredibly dangerous. They deal with lethal voltages, so you can't just have anyone tinker with them. There are absolute golden rules. They must only be installed and maintained by certified, highly trained engineers. Every single connection has to be tightened to strict specifications. Systems must be thoroughly tested before ever going live, and rigorous high-voltage safety procedures have to be followed every single time without exception. And just like that, we've decoded the whole thing. Just minutes ago, the original blueprint might have looked like an overwhelming wall of tech specs, but now, you know exactly what a vacuum circuit breaker is, you know the eco-friendly advantages of the vacuum interrupter, you know the mechanical anatomy, that incredible 4-step breaking process, the draw-out installation methods, and exactly how they protect everything from our hospitals to our train networks. It really makes you look at the world differently, doesn't it? So the next time you walk into a brightly lit hospital or board a high-speed train, take a second. Will you think of that silent mechanical vacuum standing by in the dark, ready to catch a 36,000-volt surge in a fraction of a second to keep your city's grid safe? I know I certainly will. Thank you so much for joining me on this explainer. Stay curious and keep learning.